Okay, so a common measure of how long a decaying, for example, a radioactive sample lasts, and how fast it's decaying, is the time it takes for half the original sample to have decayed. And this is the half-life, and I'll denote it as T1 half. Okay, so we're going to start looking at what half-life is and how we can do some calculations with it by looking to our equation for decay. So we've got, well, how much of our population is left if we start with n naught, and we've got this exponential decay term where we've got our time passed and our tau term, which is our kind of mean lifetime time scale. So at this point, we're going to have half our original sample. So n becomes n naught over 2. And our t term is going to be t1 half minus t1 half over tau. So this is at our half-life point. So these two cancel, and so we get 1 half on this side is equal to our exponential term, t1 half over tau. Okay. Now I want to get rid of this exponential, so I'm going to take the ln of both sides. So I'm going to have here, I'm going to have ln 1 half is equal to ln of e to the negative t1 half over tau. And I can bring this exponent down. I've got ln 1 half. And here we're going to have negative our t half over tau. Okay, so now we can get an expression for our half-life in terms of its relationship with tau. Okay, so that's quite useful. Now we can also take that result, combine it with our existing equation. So we can rewrite our equation for this decay process in terms of this half-life. Okay, so how are we going to do that? Well, we start with what we've got. We've got n is equal to n naught e to the minus t over tau. But we have now an expression, so we're going to substitute in tau is equal to t1 half, should be a negative sign here, over ln of 1 half. That's coming from here. We're just isolating tau, bringing this ln 1 half down here. Well, now we have n is equal to n naught, and our exponential is going to get a little busy. So we're going to have negative t ln 1 half. Just trying to keep that off to the side here. That's how we went from one step to the next. Negative t 1 half. Okay, so what I've done there is just substitute in this expression for tau. Now it's a little busy, but this is going to get simpler in a moment. And two negative signs immediately are going to cancel. So we'll just rewrite it without that. And not e. Now I'm just going to have t over my half-life, t1 half. And I've got this term ln 1 half here. Okay. Well, to make this a little easier to work with, we're going to use an identity, which is a to the x is equivalent to e to the ln A times X. So if we look at our format here, our E term, we've got this ln 1/2. So the 1/2 is going to be A. So A is going to become our base. And then we've got this term here, the T over T 1/2. That's our X, and that's going to go back up into the exponent. So what we end up with now is n is equal to n naught. We've got a 1/2 as our base, T over T half, so our half-life. Great. So now we've got a new equation for this decay process that is written in terms of the half-life. So now we can find out how many is left at a given moment in time, knowing just the starting population, time that's passed, and the half-life. Now I just wanted to give you a sense of this. So examples of half-lives. Well, in the advanced physics labs, we have some radioactive materials. And some examples of those are we've got some polonium-210, and that's got a half-life of about 138 days, which means I'm going to have to buy more every couple of years because it disappears. I've also got some cobalt-60. The cobalt-60 has a half-life of about just over 5 years. So that's much longer lived. I will eventually probably maybe have to replace that. And we've got some cesium-137, and that's got a half-life of about 30 years. Now, there's a few other examples that are worth noting that we're actually going to think about for dating things, so radiocarbon dating. The most common one that you hear about is carbon-14, and that's got a half-life of about 5,700 and some years. So of course this is also giving you a sense of, well, how quickly do they decay and how long can I get a signal out of this? You know, if you've got something that's going to be more than 10,000, 20,000 onwards years, you're not necessarily going to have a strong signal from your carbon-14. It'll have all started to decay away. But there's other things we can look at as well. We can look at some potassium-40. It's got a half-life about 1.25 billion years. Oh, this is much longer, billion years. And if you want to go even more extreme, you could look at some uranium. Some uranium-238, and that's got a half-life of about 4.5 billion years. So there you go. Now we've got another way of looking at how quickly a decay process is occurring and how much of our original sample is decayed away.